We have our final presentation from Innovation Crossroads. Co-founder and MIT professor of engineering, Desiree Plata, will be presenting on behalf of Megan O'Connor. Megan O'Connor is the actual innovator. She couldn't make it here tonight. So we have the next best thing, the professor, right? It's a reminder, by the way, the genesis of a lot of these projects, not all the time, but a lot of the time it's the university setting. And so Desiree's here, and she's going to talk about Nth Cycle, how they are developing an innovative and much-needed paradigm shift in electric materials for recovery and reuse. Please welcome Desiree.
Thanks, John. Thanks. Nth Cycle is committed to creating a new domestic supply of the metals that empower most of the advanced technologies that you see around you right now. In particular, I'm talking about rare earth elements and specialty elements like lithium, cobalt, nickel, and magnesium. They might be sitting in the cell phone in your pocket, the laptops you see powering the displays around the room. Maybe you're wearing some on your wrist. They're also essential to enabling a transition to a clean energy economy. They're critical components of the majority of wind turbines, as well as in clean, hybrid, and electric vehicles. I'm going backwards. There you go. Now, the problem and the major limitation to continued production of these advanced technologies, especially for US-based manufacturers, is that we are 100% reliant on foreign imports to supply these rare earth and specialty metals. And that reliance leads to price volatility and a critical supply bottleneck. Not only does that create a vulnerability with respect to national security, but it also gives rise to a major environmental risk. Less than 1% of rare earth elements are recycled, and functionally 0% of lithium-ion batteries are recycled each year. This leads to liability in terms of chemicals leaching into soils and groundwaters, as well as translates to billions of dollars in critical materials literally being left behind in the dust. We think we can do better. And that's the Nth Cycle innovation, to try and come up with an economically competitive way to recycle metals, finally and once and for all. Now, several years ago, we wrote an article, and us academics like to think that major corporations read our articles, and we identified 8 technologies that were needed to really enable a transition to a circular economy in the electronic sector. And lo and behold, in parallel with our own encouragements, major players in this market space were actually working on some of these technologies. Consider Apple, for example. They've already instituted a buyback program that outcompetes secondary markets for your cell phones, laptops, and iPads. They also invested substantially in creating a series of robots that can disassemble those devices into their individual components. And that's where they get stuck, with bins of parts. And that's where Nth Cycle comes in. Our technologies can recover the rare earth elements and specialty elements from these devices into a form that's directly reusable in manufacturing. Now, many of you are sitting around the room and saying, no, I've been recycling aluminum cans and copper pipe for a very long time. Why can't we recycle metals in electronics? And one of the reasons is that electronics are implicitly hazardous, particularly the lithium-ion components. And that translates to high risk, high cost transportation to centralized waste processing facilities. We cannot use the same metal manufacturing waste recovery technologies for bulk metals as we want to for these technologically advanced materials. So if we take, for example, a spent lithium-ion battery in upstate New York, that has to be transferred to what we might call a tier 1 recycler here in the Midwest. That tier 1 recycler is responsible for the sorting and manual disassembly of these materials into bins of parts. Those parts are then at a high cost transferred to another storage facility and then transported yet again, often overseas, to a processing plant that can actually get back value from those materials. And then the US-based manufacturer pays to repurchase those materials that they once owned a second time. All of that translates to high capital expense, high operating expense, and it tends to be very space intensive. The economics of this just doesn't work. You can't recycle technologically important elements in this way. And that's where Nth Cycle comes in. So what do? We take really an old idea, electrochemical recovery of metals. Here I'm showing an electroplating facility, and for a sense of scale, that's a person. On that side, I'll show you him here. So if we assume he's 6 feet tall or so, these are enormous operations. They rely on large surface areas, often of stainless steel cathodes, and you can apply an electrochemical potential there to recover something like copper, aluminum, or nickel. And you can do that because those are bulk elements that are present in large quantities, so you can do that competitively. Now what we want to do is shrink this process down, and we use nanotechnology to do that. In particular, we rely on carbon nanotubes, which can have hundreds to thousands of square meters of functional surface area per gram of material. That allows us to take this operation, which is the size of a cubic football field, and shrink it down to the size of a home water filtration system. This means now that we can stack these in series or in parallel, apply specific voltages to recover the metals we want, discriminating the bulk from the rare earth elements, and we can put it anywhere. This is economically competitive recycling. So if we revisit that spent lithium-ion battery in upstate New York, it now can be transferred to that Tier 1 recycler, and our device can be deployed on-site at the Tier 1 recycling facility. That's no more significant capital investment, no more expensive hazardous transport fees. And we can recover the value-added materials directly from that spent electronic waste facility. Here's a picture of our pilot scale device, and what you're looking at are neodymium oxides precipitated on the surface of a functional carbon nanotube-based electrochemically active filter. So we have dwarfed the capital expense costs. We have a 5-fold reduction in operating expenses. We have a modular design that alleviates the need for transportation. This is finally economically competitive metal recycling here in the United States. Today, Nth Cycle is focused primarily on the automotive and advanced electronics industries. In particular, we're focused on recovering rare earth metals from the permanent magnets that are present in speakers and motors in electric vehicles. The projected market size for 2025 is $20 billion. It is unclear how much of that could come from recycling because it's not been done at an economic advantage before. We're also focused on recovering cobalt, nickel, and manganese from batteries that are present in electric and hybrid vehicles, as well as in cell phones and advanced electronics. Today, this is in 2025, this will be a $56 billion market, and the recycled content there is valued at around $20 billion. We have been on target to meet the technological milestones to this lucrative market. It started with Megan O'Connor's PhD work in 2017, which completed in 2017 when the company was founded. We then were able to win Innovation Crossroads funding, and we've been able to use that to build the pilot scale device that I have on display today. We then recently won SBIR seed funding and have opened a facility in Boston, closer to myself and some of our colleagues, and we're partnering with the 2 largest Tier 1 electronics recyclers in the United States, Retrieve Technologies and Battery Solutions, to try and demonstrate that we can use our devices today in an economically and technologically competitive way. This is our team, and I hope you will join us in our mission to supply sustainable, secure energy fuel that adds to a productive U.S. economy.
Thank you, Desiree.